All right, in our last video, we discovered the first fundamental theorem of calculus and got a little bit of a sense about why you would evaluate the area under a curve by taking the antiderivative of that curve, evaluating the antiderivative at the two endpoints, and then subtracting those two values. We used that motion example, and hopefully that made a little bit of sense. All right, so this video we'll just go through a few examples to get used to the mechanics of using the first fundamental theorem of calculus to evaluate definite integrals. So when we have our integrand of 8, we're going to take the antiderivative of 8 with respect to t and get 8t, right? So the idea is that when we take the derivative of 8t with respect to t, we get 8. We're undifferentiating or anti-differentiating. And we're going to evaluate that at 1 and at -3, and we'll subtract those two. So we're going to evaluate 8t when t equals 1. We're going to evaluate 8t when t equals -3, and we're going to subtract the two. So that's going to be 8 minus -24, which is 32. And a graph would be very illustrative here. We'd see a rectangle, right, whose height is 8 and whose width is 4, and the area is 32. So some more complicated problems. We've got inverse power rule going on here. So remember that we have to undo the power rule. So the 3 bumps up to a 4. We'll divide by 4, so these 4's cancel out, and we'll get x to the 4th, right? If I take the derivative of x to the 4th, I get 4x cubed. Same thing with this. I'll bump the 2 up to a 3, divide by 3, the 3's cancel out, I get x cubed. If I take the derivative of x cubed, I get 3x squared. So all that is good. We will take that antiderivative, evaluate it at our endpoints of 3 and 1. So when we evaluate that at 3, we get 3 to the 4th minus 3 cubed. When we evaluate at 1, we get 1 to the 4th minus 1 cubed. And then we'll subtract the 2. So this is 81 minus 27 minus 1 minus 1, which is 0. So 81 minus 27, subtraction is hard. So we'll subtract 30 and go down to 51 and then add 3 to get back up to 54. All right, so that would be the area under the curve. You can always double check these in a calculator as well. So it's worth playing around with that. Get a little tricky with it here and try to take the antiderivative of this. So let's see, the cosecant squared function is the result when you take the derivative of the cotangent function. So we're not going to use any trig identities with this 2. We'll just treat that 2 different separately. So we'll do 2 theta, right? The variable here is theta. And then I think we'll get a positive cotangent of theta, because if you took the derivative of positive cotangent of theta, you're going to get negative cosecant squared of theta. So that looks reasonable to me. And then we'll evaluate this at pi over 2. And we'll evaluate this at pi over 4. We will subtract those two, and we'll call it a day. So 2 times pi over 2 plus cotangent of pi over 2. And then we will subtract 2 times pi over 4 plus cotangent of pi over 4. All right, well, 2 times pi over 2 is pi. Cotangent of pi over 2 is 0. 2 times pi over 4 is pi over 2. And cotangent of pi over 4 is 1. So we are subtracting the pi over 2. We are also subtracting the 1. Don't forget your basic algebra here. So pi minus pi over 2 is pi over 2, and 0 minus 1 is -1. And that should be your final answer. Great. So how do you deal with absolute values? Well, remember that absolute values are always positive. So that would mean that this function is going to bounce off of the x-axis when the argument of 2x minus 6 is equal to 0. So if x is equal to 3, then 2x minus 6 equals 0. So we're going to break this up into two different integrals. The one that's going to go from 0 to 3 and then another one that's going to go from 3 to 4. Now the question is, what are we going to integrate? So again, how did we find that 3? That 3 was a special value that we found by setting 2x minus 6 equal to 0, so x equals 3. So if x is less than 3, let's say it's equal to 0, I would get 2 times 0 minus 6, which is negative 6. Take the absolute value of negative 6, and that's going to flip the sign. So when we're integrating from 0 to 3, we're talking about values that cause the argument to be negative. So we're going to have to take the opposite sign of that. So we'll do a negative 2x plus 6. And if you look at a graph, that's actually what the left half of this V graph is going to be, right? It's going to be that line, negative 2x plus 6. When we use values bigger than x, like 4, bigger than 3, like 4, for example, 2 times 4 is 8, 8 minus 6 is positive 2, so the absolute value of positive 2 is still just the same thing back again. So this is going to be the same thing back again of 2x minus 6. So these are two separate problems that we're going to do. Now, I would point out that this is kind of a tedious problem, so maybe it would make a little bit more sense to try to graph this. So at x equals 3, we've got our vertex, and we've got a slope of negative 2 going that way and a slope of positive 2 going that way. Our integral is going from 0 to 4. So we've got this triangle right here, whose height is 2 and whose base is 1. We've got this triangle right here, whose height is 6 and whose base is 3. I'm finding those values by using the function. And so we've got the first triangle is going to be 1/2 base times height, which is 1/2 3 times 6. And the other one is going to be 1/2 1 times 2. And if you see these shortcuts, then use them, because that's a lot easier than taking the antiderivative here and the antiderivative here and then doing the subtraction for each of these two things. But I would recommend doing it both ways, at least to begin with, to make sure that you're getting the same answer. Whenever you can do a problem two different ways, and you get the same answer both times, then you can feel fairly confident that you, A, understand the material very well, and B, your answer is correct. So unfortunately with this quadratic, since it's curvy, unlike this straight edged V that we have for this graph, this is going to be a parabola that gets bounced off of the x-axis. We're not going to be so lucky as to be able to use triangles to find the area here. I think we're kind of stuck using the fundamental theorem of calculus here. Unless you want to go into Simpson's rule, but I don't want to do that. So do the same idea here. We're going to ask, when does that argument equal 0? Well, that factors to be t minus 1 and t minus 3. So at t equals 1 and at t equals 3, our argument equals 0. So those are places where it bounces off the t-axis. So notice that our integral is only going from 0 to 2. So we don't really care about that t equals 3. We only care about the t equals 1. So we're going to break this up into two integrals from 0 to 1 of something. We don't know quite what yet. It's either our original argument or negative our original argument. And then also from 1 to 2. So the question is that argument positive or negative when t equals 0? Well, 0 minus 0 plus 3 is positive, so we're actually going to keep the positive version here. But then if we evaluate this parabola, this quadratic at t equals 2, we're going to end up with negative something, negative 5 maybe, I don't know, 4 minus 8 is negative 4 plus 3 is negative 1 actually. So it's a negative value, so we're going to flip all the signs so that t squared becomes a negative t squared, that negative 4t becomes a positive 4t, and that positive 3 becomes a negative 3. And we're kind of stuck doing this the long way. So t squared integrates to t cubed over 3, 4t integrates to 2t squared, and 3 integrates to 3t. We'll evaluate that antiderivative at 1 and at 0, and then we'll add. Don't reinvent the wheel, just flip all the signs. We already know what that's going to be. Just flip all the negatives to positives and all the positives to negatives, and we're going to evaluate this at 2 and at 1. So evaluating at 1 here, we get 1/3 minus 2 plus 3. 1/3 minus 2 plus 3. Evaluating this as 0, we get 0. So that's nice. So that is the integral from 0 to 1 of the positive argument. And then we'll add to that the integral from 1 to 2 of the negative argument. So evaluating this at 2, we're going to get -8/3. Plus 2 times 4 is 8. Minus 3 times 2 is 6. And then when we evaluate this at 1, we're going to get -1/3 plus 2 minus 3. -1/3 plus 2 minus 3. All right, so simplifying this up, we get in this first parentheses, we get, let's see, that's going to be 1 plus 1/3 is 4/3 minus 0 plus, let's see, this is going to be 2 minus 8/3. So that's going to be 6/3 minus 8/3, or -2/3. And then we're going to subtract whatever we get over here, and this is going to be 2 minus 3 is -1, minus 1/3 is -4/3. So subtracting a negative is adding, so we have 4 minus 2 plus 4 is going to be 6, so 6/3, which is 2. And hopefully, if I didn't make any mistakes, then 2 is your exact final answer. I'm going to go ahead and check that in a calculator real quick. But if I'm correct, then this is the end of the video.